Now in this session I've had to move the tripod. We're now in a regime, custom. I have a much bigger board, remember, 2.4 by 1.2. So this rectangle you see here is just 1/4 of the board, and I'm now talking about the third quarter. So these squares, they're 0.6 of a meter, 60 centimeters square. So this is the fifth and the sixth. So two squares per session, 4 sessions per board. Right? And this time I've got myself a little stool so I can sit when I have to talk about this side, but when I'm talking about this part, I can sit on the board. But I now have to take a mental note that I cannot point to something that is outside the rectangle, because you can't see it. So I had a look at the previous 2 sessions that I just recorded, and everything is bigger, and so I hope much clearer. So I hope I've finally licked the readability problem by just basically making everything bigger. And the zoom seemed to work, so I'm not quite sure whether I'm going to, well, I probably will anyway, but whether I really need to go to very high definition or not. Maybe this is now sufficient. Well, we'll see. I mean, this whole thing's an experiment, right? All right. Well, continuing on. I have a lot of books just here. I'm going to have to move them, I think. I don't quite have enough room. Yeah, I'll definitely have to keep innovating here. Okay, so we're talking about now, we have a free particle coming in from the left, okay, and it hits a finite potential barrier of size V0, positioned at x equals 0 at the origin. And we had on the left part, that means x is negative. We had a wave function. You can't see it's in the previous square, but I'll just read it out to you. So it's u over 1 over root L a e to the ikx plus b e to the minus ikx. So this a and the b, from the previous square, previous session, just look on a as an amplitude of the wave moving to the right, and b might be a reflected wave moving to the left, right? So it'd be like a left moving wave, right? And that's on the left. That means the region in one-dimensional space where x is negative, less than 0, right? Okay, now let's do the same thing on to the right of the barrier, where the barrier starts. So positive x, so x is greater than 0, and we'll solve the STI, the Schrödinger time-independent equation, and it's of this form. Okay, now we do have a potential. It's V0. Okay, so it'll be minus V. And the solution to this will be of this form. Again, the 1 over root L thing. I asked you, to do this for homework. So this refers really to, well, this. You find this solution for the Schrödinger equation. And K dash is of this form. Now again, is that correct? K dashed? Is it? Sorry, I'm just wondering if I've made a mistake. Is it IKX? Let's check that I've got that correct. Yes. Yes. Okay. I was having some doubts there for a moment. So for homework, check that this is the general solution to the Schrödinger equation of this form. Now why is it I? I suppose this minus, got a plus V. Okay, all right. Where k dash is this, that's fairly usual. Now let's assume now that the free particles, this beam of free particles, if you like, free waves, is coming in from the left only. So in other words, there are none coming in from the right. So so if they're coming in from the right, your x here would be so the x is positive. So you don't want this term to be here, because that would be, if they're coming from the right, your k dashed, that's think of as the wave number, that would be minus k, minus k dash. So now the plus k dash is coming from the left to the right, coming this way. But it is going the other way, but we assume that doesn't exist, right? So make d naught. So kill this term, right? So oh, and this symbol here, it looks like a capital E mirrored. That's from mathematics. It's a very commonly used symbol in math and logic. It just means there is, or there are, and putting a slash through it. So it's mathematical shorthand. So it means if there is no, or there isn't, or there aren't. Right? So if there's no flux coming from the right to the left, so there's no flux coming this way. Right? So your d is naught. Right? So now you have two wave functions. You have this one to the right of, in other words, x is positive, to the right of x is 0, and you have the other one in the previous square, valid for where on the left part where x is negative. So those two at the barrier at x equals 0, you then apply your usual constraints of wave functions. The usual single valued, normalizable. Have the two wave functions either side of the barrier. They have at the point x equals 0, they have to have the same value, and their gradients at that x equals 0, those two gradients have to be the same. Okay, so we have two wave functions. So at x equals 0, this wave function and the previous one, previous square, they have to be equal. So I ask you to do that for homework again. A lot of increasing amount of homework, right? So just prove that a plus b, d's naught, that a plus b equals c, right? The two wave functions have to be equal at x equals naught. So that's where this one comes from. So prove that. That's pretty trivial. Now you got your two wave functions. Differentiate both of them with respect to x, and at x equals 0, equate the two gradients. And if you do that, you will get this expression, right? K into a minus b equals k dashed c. Right? You got k dashed here, where this is k dashed. If v is naught, you've just got square root 2me over h bar squared. That's just k, right? But now we've got a potential, so we're talking about k dashed, not k, right? Okay, so you have two equations. A plus b is c, and the second one, and so we have two equations and three constants, a, b, and c. Now you can solve for b over a, and you can solve for c over a. Do that, and you'll get, in terms of k and k dash, you get these expressions. So do that for homework, right? Solve for b over a and c over a. Now, why are these interesting? Well, we'll square them in a moment, and then we'll interpret the square values as proportions of the wave. How do I put that? The flux, I guess, that gets bounced back and gets transmitted. Okay. So A is the amplitude coming from the left, B is the amplitude going back to the left, in other words the bouncing part, and C is the part that gets transmitted. It keeps coming from left to right into the barrier part, where X is positive. Okay. Now these three terms, 1 over root L A I e to the kx, which is the previous, similarly on the previous square, and this third one here, which is this one here. Those three correspond to like current densities. So a bit of a reminder, what is a current in this context? Think of it as it's just the probability density per second. It's sort of like the flow of probability. If you have a sort of surface, well, let's say you're talking one dimension, so with your x-axis, and here's a particular point, and over time that probability will change. It's a function of time, let's say, and position, but you're at a fixed position. So over time that probability will change. So if you differentiate that probability with respect to time, that's your sort of flow of probability, and look on that as current. Right? Like if your probability density